Hello, we are Will, Kate, Faith, and Ohm, and together we form the Microsoft Capstone Group. For the past couple months, we have been hard at work on a problem that farmers often face, that being what to do with large data sets. It has been a recent trend to outfit anything and everything with sensors, and this trend has certainly not passed over agricultural producers. The data set that we are working with came from a farmer who had their combine outfitted with GPS, soil moisture, and yield flow sensors. Every 1 to 2 seconds during their harvest, these sensors take readings, which is stored in a large CSV file. These large data sets are complicated and perplexing, and mean nothing to the farmer unless it's presented in a way that can inform their business decisions. The farmer needs a clear picture of the relationship between these metrics. This problem lies at the intersection of data science and agriculture, and solving the problem requires expert knowledge from both areas. Microsoft's suite of analytics tools is up to this difficult task, clearing the mist around data analytics to provide clear visuals and prediction models fine-grained enough to inform farmers' specific business tasks, like planting and fertilizer application. Our process first involves cleaning and prepping our data using specialty GIS tools. With this clean data as well as supplementary climate information, we create visualizations using Microsoft's Power BI Business Analytics tool. Then, using Microsoft's Azure machine learning capabilities, we built and trained an ML model to predict yield given certain soil type, elevation, and weather information. The first stage of the data pipeline is to clean and prep this data. Due to instrument inaccuracies, terrain irregularities, as well as hiccups in the crop flow through the combine, there are errors in the data. Our solution to this problem was to define an upper and lower bound on the yield and throw out all data points with yield outside of these bounds. We chose the lower and upper bounds to be the mean plus or minus 3 standard deviations. After we cleaned the data, we subdivided the field into 20 by 20 meter squares and calculated the mean yield within each square, as well as the mean elevation and mean soil moisture. Now, in addition to the data from the combine, we supplemented our data with that from miniature weather stations. Here in North Dakota, there is a network of these stations hooked together through NDSU's NDON project. We gathered data from these stations through NDON's website, choosing the station that is located closest to the farm field we are concerned with. From this data, we gather a few different metrics. First, we divide the growing season into 3 intervals: the vegetative phase, the reproductive phase, and the mature phase. Then, we gather the total rainfall and average temperature for each stage of the plant's life cycle. In addition to these basic metrics, we also took the potential evapotranspiration, which measures the amount of crop water loss. Now, while GIS applications do have some basic graphing capabilities, other applications are better suited for this task. Power BI is Microsoft's powerful visualization tool capable of creating user-friendly graphs and other illustrations of data. With these tools, we are able to create statistical graphs as well as geospatial mappings of our farm field. Here we have a box and whisker plot showing the relationship between elevation category and yield. And here we have another showing the relationship between yield and precipitation during the vegetative stage of the crop's life cycle. And here is a geospatial rendering of the farm field, again created using Power BI. High yield is represented using darker colors, low yield with light colors. While the farmer is certainly interested in descriptive analytics, they are also interested in being able to predict future yields. This is where Microsoft Azure comes into play. Azure is Microsoft's cloud platform, and one of its services is machine learning. There are actually 2 services, one that is entirely code-based and another one that uses a drag-and-drop UI. The data science amateur is most at home with ML Studio, which allows the user to quickly configure, train, and deploy machine learning models. However, the accuracy of the final models are sacrificed for its ease of use. There are many features lacking, such as automation of running through and testing all the different algorithms, as well as the use of hyperparameters within the algorithms themselves. The data science veteran will find the code-based approach far more accurate and robust. There are many features here in Machine Learning Service that are lacking in Studio, such as the AutoML library. Using both of these services, we are able to build models, train them with real farm data, and then predict what the yield would be given certain climatic conditions. Not only are we able to give overall yield, but we are also able to predict yield for each 20 meter by 20 meter field subdivision, which gives the farmer valuable information on how to manage their field. Now we'll take a step back and look at our development process. Most of Sprint 1 was spent learning the new platforms and applications that were needed for the project. Also, a considerable amount of time was spent making sense of the data. None of us are acquainted with farming, so we could not quickly gain business insight from simply looking at the data. Sprint 2 was where we really got down to business. We prepped data in GIS software, created some visualizations in Power BI, as well as created some models in Machine Learning Studio. During Sprint 3, we had a slight requirement change. There were concerns that the data was not adequately cleaned and prepped during our earlier sprints. So most of Sprint 3 was spent redoing our cleaning work and then resetting our visualizations and our ML models to work with our new clean data. Sprint 4 has been spent working in ML service and exploring the differences between the studio and service, as well as working on documentation and tying up loose ends. Now, of course, our project wasn't entirely without its problems. There were initial issues with setting up our Azure accounts. Also, the GIS software and learning how it worked consumed a significant amount of time. Also, the methods that we used to clean and prep our data was never fully agreed upon. The method that we chose was a compromise in order to get us moving on to our next steps. Any future work on this project will need to incorporate a new step in the cleaning pipeline. Well, that concludes our summary of our project. Before I go, I'd like to thank Dave Frostley, our sponsor from Microsoft, as well as Alex Rademacher, Dean Knudsen, and the faculty in Ag Engineering whose input ensured the success of this project. Thank you for watching.